Welcome to Algebra 2. Today we've got section 5.5, and we got a little extension of that lesson today called combinations of functions. So we've learned how to operate on functions to combine them together in different ways, but there's a specific type of combining of functions that we just generally call combination, and it involves putting one function entirely into another. So if you think about the way a typical function is represented, we have an input, and then the whole thing, f of x, is referred to as the output. So what we're dealing with today is a function being performed just like f of x, and then the result of that is plugged right into another function. And we have this new notation. It's like a little central circle here, and that is just read as of. So like when I look at this, it is f of g and then of x, just like we would have f of x from before. And whenever we're working with functions like these, evaluating them, we want to be sure to work from the inside out. So we're just going to make a little note over here off to the side that these are inside out problems. Imagine that we start with some x value, some input. If I plug it into f of g of x, and I prefer to see it this way, first that x is going to go through function g, and then that result is going to go through function f. Because once we get the output of g, that result is still the input of f. So just remember to work your way from the inside out. The process is pretty straightforward. Here in example 1, we'll go through 4 quick examples of, we have some functions f, g, and h defined up above, and then we're going to test and see what are the values of different combinations of those functions with different inputs. Now, another good rule of thumb is that if we have, you'll see in each of these cases, if we have a number going in, we're going to end up with just a number coming out. So I should have no more x's, no variables whatsoever when all the dust settles, when we finish these problems. So let's get started here on letter A. So I'm starting with this 3. That's my ultimate input, working from the inside out. 3 goes into function g. Okay, and then what's the output of that? Well, it says I take my input of 3 and then add 7 to it. So the output from function g is 10. And then I'm supposed to turn around and put that into f. So I'm trying to find f of what I just got as an output. All right, so f of 10 says I take 3 times the input. I'm just following the rules up here for what f is telling me to do. So the final result is the number 30. We put a number in, we got a number out. All right, let's try letter B. Now we're using functions g and h. So the first thing that happens is negative 2 goes into function h. What is h of negative 2? Well, function h over here tells me to take my input and square it. So I'm taking that negative 2, all of it, in parentheses, and I'm squaring it. And I know that when I square a negative number, the result is positive. Okay, so that output from h becomes the input into g. So I'm taking g of that 4. And again, the rule for g says to take the input and add 7. Final output, 11. We've worked all the way from the inside out. Letter C, we are able to run a number through a function multiple times. So here it says I'm starting with an input of 1. That goes into function h, which says to square it. So h of 1 equals 1 squared. Hey, that just equals a 1. Then that has to go through function h again. So now I'm finding h of 1 yet again. I'm taking that 1 and squaring it. My final answer is just a 1. Probably could have done a better job choosing an input for that. Let's see what would happen if we took h of 1/2. Sorry, h of 1/2. Well, 1/2 would go into h. That would mean I would take that 1/2 and square it, whatever the rule for h tells me to do. And that equals 1/4. Okay, so then when I go through h the second time, I'm taking h of 1/4. And that means I take that input and square it. I just follow the rule that h specifies again, and I get 1/16. for a final answer. So just kind of extending the idea, make sure we understand how to work our way all the way from the inside to the outside. And then letter D, take a look at all that's happening here. I strongly encourage you, if you see this notation with all the circles, to change that into multiple parentheses like we saw in A, B, and C. It's so much easier to follow it from inside out if we have it that way. So I have f of g of h of 2. So a lot of things happening. We got an extra step as we go from the inside out. Let's see what happens. So the inside thing is to take a 2 and plug it into h. What is h of 2? Well, the rule for h says to take that input and square it, so that's a 4. That result then has to go into g, so g of 4, and my rule for g says to take that input and add 7 to it. That's 11, and then that result goes through function f of 11, and my rule for f says to take 3 times the input, so 3 times 11, and we get 33 for final output. Even though we had 3 functions involved, a number goes in, a number comes out. All right. Example 2 says to find g of h of x and h of g of x. Now, what we're going to do here is we're going to kind of experiment and see if the order matters or not. Well, if my input is going through both functions, does it matter what order I do that? And let's just let these examples speak for themselves and see what happens. So you'll notice as well that I'm trying to find g of h of x. There's no number going in, so I'm going to end up with more than a number coming out. I'm going to end up with some expression with x in it. But x should be the only variable. I don't want to see any g's or h's at the very end, just something x, or something with x involved. So first let's do, and again, rewrite this, g of h of x. Well, the inside thing is h of x, and hey, they tell me right here what h of x is. It's 3x minus 4. So if I'm looking at the inside thing first, that's g of 3x minus 4. I just kind of substitute it in. Okay, so what is function g telling me to do to this input? It says to take that input times 2. So 2 times 3x minus 4. And here we just need to distribute to simplify it. 6x minus 8, that is our result. Now we also need to do h of g of x. And this time what's inside is g of x. That's 2x. So my input to h is really whatever g of x is equal to, 2x. Okay, so I take that 2x and I run it through function h, which says to take 3 times that input and then subtract 4. That's 3 times 2x, then subtract 4. I get 6x minus 4 for an answer. So I caution you against trying to find too many patterns here. You'll notice we ended up with different answers based on the order. The order does not produce the, changing the order doesn't produce the same thing each time. That's not a pattern we can rely on. But even seeing like the 6x, we can't make assumptions that that type of pattern will emerge every time either. And hopefully you'll see what I mean here in letter B. So first thing we need to find is g of h of x. What is h of x? Well, it's x squared minus 6. So that inside thing, still working from the inside out, means I'm taking g of x squared plus 6, all of it. And my rule for g says to take that and add 5. Whatever my input is, I add 5 to it. So I take my x squared plus 6 and I add 5 to it. Combine some like terms and we end up with x squared plus 11. Don't want those to mix together. Now what happens if I do h of g of x? Well, g of x is x plus 5. So I'm really taking h of that x plus 5. When I plug x plus 5 into function h, it says to square the input and then add 6. So I take my input, x plus 5, as a quantity, square it, and then add 6. And here we have a little bit of foiling to do. Nice that we have that little shortcut for expanding binomials to the second power. And then we can combine like terms. X squared plus 10x plus 31 is our final answer. Take a second to notice, though, that in each case, the final answers were just expressions with x. There were no g's, no h's in there. Those were just telling me what rules to follow. Ultimately, I'm just working with expressions that have x in them. Okay, our final example is how does this apply to real life? And really, one of the best situations is multiple discounts. I think this makes total sense. So Chloe is shopping for a new pair of jeans. She finds a pair that costs $59.99, but it's on sale for a 20% discount. She also has a $10 coupon she can use on the pair of jeans. Letter A says we're going to come up with two different functions, P of x, which is the price after the discount, and C of x, the price after the coupon has been dealt with. So let's define those two functions. P of x equals, and let's just think, if they are taking 20% off the price, that means I'm left with 80% of the price. So I'm going to call that 0.8x. If x is the original price, then what the price after the discount is just going to be 80% that's left over of that price. So 0.8 times x represents 80% of the initial cost. And then C of x, let's let that equal the coupon. Well, if I have a $10 off coupon, that just means we take the original price and subtract $10 off of it. Okay, so letter B says find and interpret C of P of x. Okay, well, C of P of x means I start with P of x on the inside and then run that through C. Okay, so I'm taking C of 0.8x, and if I put 0.8x into function C, it says swap out the input with 0.8x and then subtract 10, 0.8x minus 10. Now think of the order that we followed here. The order that we followed is that we did P of x first and then C of x. So what this represents as far as interpreting it, the interpretation is that this is what the cost would be if discount was first and coupon was second. All right, and then letter C says find and interpret P of C of x. So we're switching the order that we work through these two functions. C of x is x minus 10. So I'm really trying to find here P of x minus 10. Okay, and what does function P say to do? It says take 0.8 times your input. So that's 0.8 times x minus 10, which I guess we could simplify to 0.8x minus 8. All right, and what does that mean? That's the cost of the jeans if the coupon is taken off first and then the discount was second. So by changing the order, we're adjusting what we're doing to the price. Right? Now, if we had to extend this idea further and say, if she had the option to use the coupon first or second, what would be the better choice for her? What's going to get her that pair of jeans at a cheaper price? I think we can pretty clearly see that the first one is better, right? Because we take 80% of the price, then subtract away 10, whereas the second option, we would have 80% of the price, and then we would only take away $8 afterwards. Okay, we could actually calculate those if we wanted to, just using the input, swapping out our x with that $59.99. But the idea of plugging one function into another function is something that comes up an awful lot here at the end of Chapter 5, but also moving further into math. Definitely something worth spending a day to revisit. So hope you've enjoyed this lesson. The homework assignment is a worksheet. It is posted on the website. That does it for Section 5.5, Part 2.